All right, hey everybody, welcome back. In this video, I'm going to take you through looking at our AI and trying to make it a little bit smarter. So we'll look at a greedy algorithm and we'll talk about why that doesn't work. And then we'll look at an algorithm called MinMax. So right now I have this set up just to give us a really simple example where white here has I guess three possible moves. They can move their C pawn forward one, they can move their D pawn forward one, or they can capture. And there is a best move in this scenario, right? Because if I were to move my C pawn forward, then black can retaliate with the capture here, and then they're up 2 pawns to 1. Whereas if I move this forward, then black can't capture me. They can move forward, but I'm not losing material that way. Or I can capture and then they can capture back, and when we're still even in material. So how do we decide which move to make and which move is best? So one of the things we're going to look at is just from a material standpoint, having an AI concerned with what's my best move, what's the best way to grab the most material. So in this case, there's two out of the three moves end up with equal material, and one move ends up with white down material. So if our AI is playing white here, we would want it to pick either this move here, which results in, or sorry, that would be the move we would want to avoid. We'd want it to either pick this move here where it captures and trades, or we would want it to pick this move here where it moves and it keeps even material. But we would want to avoid this move where black can capture. All right, so there's a few things that we have to consider in order to get our program to think in this way. All right, so what we're going to start out is we're going to start with just a greedy algorithm. And the greedy algorithm is going to be, let's look at all of our possible moves. And at the end of that move, we're going to just see how can we win the most material. So a greedy algorithm in this case would look at this board and say, the best move out of my three possible moves is this one right here, because this wins a pawn. I am now up 2 to 1. Now with chess, we need to look more moves in advance. So obviously we would then need to look at black's possible moves and say, well, black can do that and they can capture, and we really didn't gain anything. But a greedy algorithm will look at, even if we did a greedy algorithm 2 moves in advance, what it'll do is it'll look at all of black's possible responses to this move. And one of black's possible responses is to push their pawn as well. And in that case, white would evaluate this as, oh, this is the best position. This is the best possible result of all my combinations because I'm up 2 to 1 after black's next move. And so we want to add in something into our AI that will also evaluate the board from black's position and pick black's best move as well. And this is where the min-max comes into play. All right, so just try to give you an example here to explain this a little bit, and hopefully I did that. So let's get into the coding. We might revisit this example in a little bit. All right, I just added in this board here. I'm just going to go ahead and comment this out. What is it? All right. And I'll keep that there in case I want to use it later for an example. All right. Now, when we left off in the last video, we had set up our AI and it's ready to go. It is, we can play with this true and true to make whether it be a human or an AI, and then we had it set up so that it will find a random move at this point in time. All right. So what we want to do now is we want to modify this. Instead of calling a random move, we want to now try to find a better move. Okay, so I'm going back over to my Smart Move Finder class where I have find random move and I find best move. And so we're going to focus on this find best move in this video. All right, so the first thing that we want to do is we want to evaluate all of our possible moves and try and just find what's going to give us the best board position. This is a greedy algorithm, meaning we're trying to maximize our own score. Now the question becomes in chess, like what is a good board position, and when is one side winning over another? And one thought of this is purely material. So if you look at material alone, each side starts with 8 pawns, 2 knights, 2 bishops, 2 rooks, a king, and a queen. And as pieces are exchanged, some pieces are viewed to be more powerful as other pieces. So bishop and knights are viewed to be about equal. Queen is more powerful than a rook. Rooks are more powerful than the bishops and knights, and pawns are the least powerful piece. Kings, you don't really need to give a value because you can never lose your king. It would be checkmate before that happens. So it doesn't really matter what you assign a value for the king, because it will, both sides will always have a king. But the way we evaluate a chessboard is one way to do it is via material. We count up all the pieces that are on the white has, and all the pieces the black has, and we see who has the higher score. So that's the first thing we're going to do. We're going to come up with a way to score the material on a board. All right. So I'm just going to have a little dictionary here, piece scores, that is going to be responsible for assigning a point value to each piece. So for example, my king, like I said, it doesn't matter what we assign it. So we can just assign this to 0. It's not to say that the king's not important. But you can never have the king captured. So you'll never be able to make a move that would leave you without a king. Queens are typically seen to be the most powerful piece, so they're given values of like 10 to 8 or 8, depending on different engines. I think 10 is common. That means it would be basically worth 2 rooks. Might only be 8 because it might be a rook and a minor piece, or maybe it's 9. So it's a little bit worse than 2 rooks. But we'll go with 10. You can adjust these numbers and play with them to kind of value piece strength. And then bishop and knight will go with 3 points each. And then a pawn will simply have as 1 piece. As 1 point here. A few other constants we're going to have in our engine is we're going to have a high score for checkmate. So if we can checkmate our opponents, then this is really good. So we'll make this worth 1,000 points. And this will be like our highest score, right? If we can get checkmate and we can have 1,000 points, then that's really good. We could make stalemate worth 0, because it's always better than a losing position. Stalemate is always better than a losing position, but it's not as good as winning, obviously. So any winning position, if we're winning the game and have a positive score, then we should try to avoid stalemate. And if we're losing the game, then obviously we'd want to go for a stalemate. Now we're going to treat this as a zero-sum game. So what that means is when we score the board, if it's a positive value, then that means it's winning for white, and if it's a negative value, that means it's winning for black. And so a white checkmate would be 1,000 points, but a black checkmate would be negative 1,000 points. And that way, black is trying to make the board score as negative as possible, and white is trying to make the board score as positive as possible. That's what they're aiming for. That's the goals of our AIs. And this positive and negative parity will come into play in our algorithm as well. All right, so let's write a simple method to score our board. So let's score the board based on material. All right, so here, let's just call this score material. We aren't going to worry about checkmate and stalemate at this point. This is just gonna calculate the board score based on position. We'll put in the checkmate into our best move, because we won't need to score the board if checkmate happens. Another way to do this is we could pass the game state into this function and check that variable to see if it's true at this point. I think that's fine to do it that way, but we'll separate it out later on. Since this method is simply score material, and then we can kind of plug in other scoring methods into getting the board score later on. That's something that you can do on your own. For right now, we're just going to simply score the board based on the material of these pieces here. So let's create a for loop that goes through our board, and we'll sum up the score. So we'll go through the rows in the board and the columns, or basically the squares in the row, and we'll look at each space, and we'll see if there's a piece there, and if that piece is a white or a black piece, we'll score based on that value in that dictionary that we have at the top. So if the square piece, so that would be 0, would be the letter of the color. So if that is a white piece, then we would want to add to our score. And if it's a black piece, then we would want to subtract from our score. So, and this again is this zero-sum game. What is good for white is bad for black, and vice versa. What's good for black is bad for white. And so a perfectly even game will equal 0. If white has the material advantage, then the score will be positive, and if black has the material advantage, then the score will be negative. So we access our score piece score, and we access it based on the character at square one, because that's going to be a pawn or a queen or a king. It's just going to add that to that value. Same thing, except subtraction for this part. And then if it's a blank piece, we aren't going to do anything. We're just going to skip over that. All right, so it's pretty straightforward. This can get a lot more complicated when we score a board if we wanted to score it more on position as well. So for example, a pawn in the center or attacking a center score could be worth more points than a pawn on the outside or something like that, or connected pawns could be worth more. That positional scoring is going to impact your AI. The more it can say about the position of a board, the better the AI will be. So our AI is not going to be very good. It's not going to make typical chess moves because we're not programming any of that into it at this point. Right now, it's purely looking at captures and taking other people's pieces off the board. Okay. So now that we have that, now we can start to look for a best move. Now, we're going to do this in a greedy fashion first, and that is we're going to look at all of our moves, look through them, score them, find the best one, and we'll make that move. Okay, so I'm going to start off by just let's come up with our max score. And since our max score, let's go from the perspective of black playing the AI. So we're going to put the best possible score would be like negative checkmate. And so we're going to start the max score at checkmate. This is a really bad score for black. When you're doing a maximum algorithm, you want to start with the worst possible score and then try and bring that down. We wouldn't want to start with the best possible score because then we have nothing compared to. So from black's perspective, checkmate is the worst possible score. And so we would want to try to bring that down. So what we'll do is we will go through every single move. So and we'll label this. I don't want to put a color to it because we want to be able to have our AI work for both black and white. So we'll call this player move, and basically this is the person's whose turn it is to make the move. And we'll call the other player the opponent. So that's how we'll differentiate. Player is the person that's going to make the next move, and their opponent is the person that would reply to that move. So for each of the player moves and valid moves, what we're going to do is we're going to go ahead and tell our game state to make that move. And then we're going to simply score the board. So we'll say, let's get the current score of the board. Let's score it for material based on, and game state board is the getter for our board. So we'll pass that in to our method. It'll score it and it'll return that value. And then the greedy algorithm is to simply say if that score is now in this, okay, so in this one, yeah, I guess from Black's perspective, we want it to be as negative as possible. So if that score is less than the max score, then that we would want this to become our new max score. And it's a little bit confusing that I'm using max here, but we'll fix this in a second. Again, I'm just trying to look at it from Black's perspective to start off. Sorry, I'm using my Java syntax here. And our best move at that point then would be the current player move. So we find a new top score and we keep track of that move. So best move, we'll start with none, and then we'll go through. And if we find a score that is our best score, then we will go on from there. Now, this works fine from Black's perspective, but now let's say it's White's perspective now, and we try and run this algorithm. Now, we want a positive board of the score, but we would want to start with negative checkmate, because then we would want to check to see if it's greater than this value, and that would become our new max. So because we have this parity of even and or of negative and positive for the players, we need to add in a little variable to kind of toggle this based on player turn. And so I'm going to add this in here. So we're going to call this variable turn multiplier. And this is just a variable to say, is it Black's turn or is it White's turn? Because that's going to depend on whether I'm trying to maximize or minimize the board. So the turn multiplier will equal 1 if it is White to move. Otherwise, it will be -1. And this is that notation in Python, similar to question mark notation in Java. I think it's the ternary operator or something like that. Tertiary. Something. I don't know. You can look it up. But the syntax is just shorthand, so it makes it a little bit quicker here. All right. And so now instead of setting max score to checkmate right away, we're gonna always set it to negative. And the idea here is we want to set it to negative, and then we want to maximize our score. So instead of grabbing the score for Black, it's going to be really good if this is a really negative score. And so we're going to take this and multiply it by our turn multiplier. And so now whenever it's Black to move, this value is -1, which means our really negative score is going to end up being really positive. And so then this ends up, basically it makes it so both Black and White, from this algorithm's perspective, are trying to get high scores rather than having to worry about, I want to get a high score, I want to get a low score. So this little variable handles that for us. Okay, so this is going to try to make the best move based on maximizing score based on material. We could also at this point add in checkmate and stalemate. So instead of scoring the board for material, we could check here. This is the other place you could basically check for like if game state checkmate, then that means our score should actually be like really high. Our score should be equal to checkmate. And we would still want, so after, like, this is like after you make a move and now the game is in checkmate, that means it's really good for that person. So this should be a really high score. And if it's stalemate, then it would just be 0. Right. I don't want when black to make a move and ends up in the board ends up in checkmate. That should be good for black. So we want a very high positive score. We want to make that move. And then this we can put in an else. So this is the kind of idea for adding in here. And basically what you guys can do to improve your AI is you can improve this score mechanism. If you want to put these statements inside of the score material, you can do that. And then you can return, basically you'll be returning checkmate or returning 0 for stalemate. Sorry, I created a variable for stalemate. We don't really need it since it's always 0. But if you want to add in like score position or things like that, then basically you could just modify this, and that's the only thing that changes in terms of this algorithm. All right. But now we're basically saving that best move, and now we can return it here. And we get a best move. Okay, so this is our greedy algorithm. Let's test it out. Let's see how it responds to us playing. So I'm going to go back to my main. I'm going to go ahead and I'm going to make the AI be player 2. So they'll be black, and I will play as white. So I'll set that to true and false. And then here we need to add some code in to actually call our smarter move. So right now we called it find best move. And I'm actually, well, yeah, we're going to modify this. So even though right now it should be like find greedy move, we're going to modify it later on because we're going to improve this algorithm. So now what I'm going to do is I'm going to say AI move equals smart move finder dot find best move. And then I'm going to pass in game state and valid moves. Now, if my AI move equals none, which it shouldn't ever, this shouldn't happen unless it can't find a move. So like if the next move that's going to happen is, sorry, that should be is none. If the next move is like ends up with it resulting in checkmate, then basically it won't be able to find a best move because the max score it will ever find is this checkmate. We'll get into that later. So it will just make a random move at that point. You'll see this sometimes when engines like give up. If you're playing an engine in chess and it gets to the end and you're up a couple pieces on it, it'll just make seemingly random moves that don't really make sense because it knows it basically has lost and it doesn't see a way out of it. So that's what this part is for, but it shouldn't ever call this at this point in time. Hopefully it will access this greedy move. Okay, so we'll go ahead and run it. We'll play a couple moves and see how it's responding, and we'll notice a few things about its behavior. Well, all right, I got an error here. Let's see. Key error, N. Yeah, okay. Yeah, I used K for knight instead of N. My fault. So let's run that again. And now, interesting. Ooh, that was a very, very strong move by by black. It duplicated all of its pawns. It turned its knight into 4 pawns each. Very powerful move. Okay. So there's a bug in our code. Let's figure out what it is. So I actually know what it is because I ran into this bug yesterday. And so if you want to, you could try and pause the video now and try and come up with what's happening here. So I'll give you a couple seconds to pause if you'd like to try and find it. So it's actually pretty simple. Is what's happening is we're telling black to make a move, and then I forgot to undo the move. So after we make the move and we score the board, then before we make another move, we actually need to go ahead and undo the move. Otherwise, we end up with that bug where it's basically making a whole bunch of moves in its turn, and that it throws off the engine itself. So let's make sure we undo the move before making the next move. Right, so now, all right, now it didn't duplicate all its pawns, so it's looking good. Now watch what happens if I do this. So it's gonna be greedy. So it's gonna take this pawn, even though I can capture it back. And it's going to take this pawn, even though I can capture it back. Now it is smart. So let's say I move my queen here. So I blunder my queen, and this pawn can capture both my queen or my pawn. It has two captures. It should pick my queen, which it does. So that's good. And again, if I move my knight here, it should be greedy, and it should capture those. All right, but it's only really looking one move ahead, and because none of the moves are captures that it currently has, it doesn't really think about the options that it has, because it sees all the moves as equal, as they all result in the same kind of end board position. Although I think it should be taking my pawn right now, which is interesting that it's not doing that. Let's see if it takes my bishop. Okay, that's a little bit strange. It started playing a little bit weird now. I'm not 100% sure why it's doing that, actually. It's now just letting me take all of its pieces. So it's kind of avoiding captures in some cases, which is a little bit strange. But there's some good there. It is definitely grabbing some of the pieces that we want. This might be why. This should be max score equals score. That maybe is why we should update our max score variable. That was probably the case. So now let's go ahead and test it out again. I'll give it a free pawn here, see if it takes it. It does. Now I'm going to attack its knight and see. Okay, so there again, it made an interesting decision. It saw a potential move was to capture this pawn. And so it says, this is good for me. I gain a pawn. But what it fails to look at is any of my retaliatory moves, which in this case, I can capture it with my rook, right? And so it's not looking yet at my moves. But if I hang a piece, it is going to grab that piece. And okay, now it's looking much smarter here. So it's if I just like hang some pieces, it will capture them. All right, so I'm going to try and get it to see if it will go for checkmate here. I have to kind of get one move away, so it might be hard for it to find it, because I might have to put my king in immediate danger. It's not going to let me. Okay, so we see some issues with only looking one move ahead, but it is working in terms of material. It is going for the best possible move in that regards. So let's make it a little bit smarter. Now, the issue with just, okay, well, why don't we just look 2 moves ahead and then score the board and find the best move 2 moves ahead? So the issue with that is, well, we don't want to just look 2 moves ahead and find the best board state for black, because this is going to assume that white has made a bad move. It's back to that very beginning example that I gave. We want to try to maximize our score while minimizing our opponent's score, right? So basically what we want to find is we want to find the minimum of our opponent's maximum possible scores from their possible moves. All right, so let me try and illustrate this a little bit. The first thing I'm going to do is I'm going to go through another set of moves. So, okay, I'm going to start renaming a couple variables here because I want to be more clear about what we're actually calculating. So, I guess the greedier algorithm is, okay, well, if I'm just looking 1 move ahead, why don't I look 2 moves ahead? So basically, okay, before I do any of this scoring things, so I'll tab all that in. Let's just get my opponent's moves. So game state dot valid moves. So let's make my opponent's moves. Opponent's moves. And we'll say get valid moves. So grab all my opponent's moves. And then for each of those moves, I will make them for opponent's moves, for opponent move in my opponent's moves. Now I will try to make my opponent move. And I have to make sure I undo that move as well. But now we're too deep. So the parity of even, odd, or positive, negative has changed. So now, because of that, I now need to negate the score that I'm getting here. I need to negate this. And in 2 moves, checkmate is really bad because this means that my opponent got checkmate, right? So I'm adding now a negative sign to counteract that. And so hopefully that makes sense to you. Think about that, because now we're looking not just 1 move in front, but 2 moves in front. But the idea here is we still want to maximize our score. Now, the problem is right now, these are our opponent's scores. So this is actually going to play to try to maximize white's score, which is not what we want. But the part that's challenging with this is we need to keep track of, we need to try to minimize white scores while maximizing our scores based off of that. So I'm going to need more than just one variable for this. All right, so I'm going to go ahead and rename this. Instead of max score, I'm going to rename this opponent min-max score. Basically, this is going to be our opponent's minimum maximum score. I'm going to try and draw a little diagram here for you guys so that it might make a little more sense. All right, so I think you can see this now. So the idea is we're looking at basically branches of the game. So this is my current state. And let's just take an example, a really simple example where we have 3 possible moves. Move 1 brings us here, or let's even make it simpler, and move 2 moves us here. So we'll just make it like we have 2 moves. What we want to do is we want to find the best move, but I can't just look at it here, because if I score this and I say, okay, this is a +1 for me, but this is a 0, then I would say, okay, this is a better move. That's what our algorithm's doing right now. But what we need to do is we need to look at my opponent's moves here. So let's say my opponent makes 3 moves here. One of them winds up with the board scoring +1. Maybe they ignore your piece. One of them maybe ends up with 0, but then maybe one of them adds up with like -2, meaning that's bad for me. It's good for them. So I want, they're obviously given this choice. They're gonna, if they can find this move, they're gonna play this move. They're gonna try to play best. So we want to assume that our opponent is gonna play best. Now, in this case, let's say that their only results are 0 or +1. +1 being for good for us. Then if I'm looking at these two moves, if I look here, I'm going to pick this one because this is my best move. +1 to 0. But if I look one move in the future beyond that, I can see that if I do this, my opponent's best move is actually this, to make the board -2. And if I look a move in advance here, the opponent's best move is to make it 0. So what I want to do is I want to find the minimum of their best moves. And again, it's called min-max because we're trying to minimize my opponent's best move, my opponent's maximum move. All right, and because we're switching positive and negative signs, like I guess technically this would be a +2, and then this would be like a negative, and this would be a negative, because we're scoring it from the other person's perspective. So my opponent is going to pick the +2. But over here, if I go down this route, then my opponent's best move is just to make it even at 0. So I would want to play this move here instead of this move here. And that's what we're going to try to implement into our algorithm now. Okay, so that's what I mean by min-max, their minimum maximum score. Now, in this case, because we're going to get rid of the negative now, because I'm trying to find the smallest value. I want the smallest one of their maximums. So I'm going to start with a very large one. And then we're going to go on from there. So that's my opponent's minimum maximum score. And then I'll still call this variable best move. So this will be my best player move. Let's change it to that. And then we can switch this to best player move. We could probably refactor these variables. It would be a little bit better. Okay, so I know this video is getting long. I know this algorithm is a little complicated, but we're almost done with it, so just bear with me. All right, so we have this min-max score here and the best move. And then what we're going to look at is after we make a move, we're going to look at our opponent's moves, but then we're going to look at our opponent's max score. Okay, so I want to find out my opponent's maximum score here. And this, we're going to start at a very negative score. So negative checkmate. So this essentially is what we were doing before, but now we're doing it for our opponent. So now I'm going to find my opponent's worst move, or sorry, my opponent's best move in the state that I give them, because they have to play with the move that I make for them. All right. Let's make sure I got all my negative signs right. So checkmate, stalemate. Again, we want to try to maximize everything. So we're going to switch this back to put in the turn multiplier here, so that it's good for both white and black in this case. And just to try to make that make sense, right? This is, so let's say from black's perspective, so this value is -1. So -1 times -1 will be 1, and this will just be a high score. So if the game state is in checkmate after white makes a move, then this is good for white. So we would want this to be a very positive score. Negative is positive, so this is a very positive score. Now, from the other perspective, let's say white moves first, then this variable is 1. White moves and then black moves. So from black's perspective, this will be negative checkmate, which means it's basically really good for black. After black moves, negative checkmate, it means that black is checkmated. All right. Same thing here. We keep these as is. So I don't know that we need to change anything there. Okay. The only thing we want to look at here is now if score is greater than not max score anymore, but now we want to look at opponent max score. So opponent max score. So now I'm trying to find what's my opponent's maximum score from this game state right now. And I wonder if we have to add the term multiplier in there. There might be something with this, a bug with this. We'll have to figure that out. I think this is right, but I feel like there might be something wrong with that. I think we need to flip it every single time. Sorry. We'll see. If it comes up, we'll fix it. All right, so score is opponent max score. So let's go ahead and then switch this to also opponent max score. Okay, and then we don't want to set this to our best player move yet. So we'll go ahead and get rid of that here. We don't want that best player move set yet. But what this essentially does is it goes through all of my opponent's moves and finds the best possible move for them and basically the highest score that they can possibly get. And so when we finish looking through all of their possible moves, now comes the kind of the nice part of this algorithm. What we're going to do is we're going to check to see if their max score that we found is greater than if their min-max score, which is what we said at the beginning to be very large, min-max score, if that is larger than our opponent max score, then my opponent min-max score equals my opponent max score, and my best player move is now the player move. Okay. Let's think about that logic. I feel like one sec. I feel like I'm missing something. Yeah, I think it's fine. I guess a better way of writing this, a more clean way, is switching this, so it makes more sense that we're trying to minimize it. So instead of saying if my min-max score is greater than my max score, saying that my max score is less than my opponent min-max score. I think this makes more sense. So again, we're writing both a minimum and a maximum algorithm at the same time. So this inner for loop, if I look just here, just at this part here, I get my opponent's moves, I set their maximum score to a very low value, go through and I try and find a very high value. I try and find their best one. So I'm finding the score and I'm seeing, is it larger than my max so far? If so, that becomes my max. So I'm basically looking at all my moves, all my opponent's moves, and finding their maximum. That's what all this does here. Then I'm looking at all my moves. So for each move that I make as the player, what's the max opponent response to that? If the max opponent responds to that, so if the opponent's max score is less than their previous best score, then that now becomes my new best move. And that's now the score I want to try and get lower than. Okay, so this is now the minimization part of the algorithm, and that's why this will work. Okay, now one of the things to make this a little bit more interesting to test right now, because we're just doing score material with and kind of checkmates being the only thing, you'll see that the computer will like move, especially us playing black, they'll move like the rook back and forth after the first move, right? So we make a move and then we make another move and it just picks this because it can't see a capture on its turn, so it sees no way to gain an advantage by moving any piece because it's only looking 2 moves ahead now. So even if it were to move this, then it sees this as a capture, so it says like that's not a good move. And so it just will go between those 2 moves. Now, if we get to a point where we hang a piece, so for example, if I hang that pawn, it will find that move. Now, if I try to offer this pawn, it won't take that because it's protected by the queen. So it does see that, and so it's not going to just grab. So it's not as greedy as it was before. And if I attack it, it is going to move that knight. Right. So it is considering, but it's also looking, only at not the best possible moves necessarily. All right. So we kind of have to open it up before it'll start making more interesting moves. And then if it can find checkmate, it will find it. So there, it just checkmated me, right? Because I let it find this opportunity here. So it's getting better. One of the things we can do to just make it a little more interesting, though, is we can shuffle its valid moves so that the order that it evaluates them in, basically, if a whole bunch of moves have the same like possible value, it's just going to pick the first one that came across. So I already have the random class in here, so I can just say if, or I can just say random.shuffle my opponent's moves. Now, this isn't necessarily efficient. I don't necessarily want to be shuffling an array of values in the middle of my algorithm, but this will add a little bit of variety to the play so you can test it out and see, how it works. So now it's not always just going to pick the best move. It should pick a random move. Oh, wait, sorry, I shuffled the wrong moves. That's why it didn't do anything. I should shuffle the player moves. So let's move this into, let's shuffle valid moves instead. My fault. All right, and now we go. And yeah, so it played a different move finally. All right, so playing interesting moves. It didn't capture because of that. It did go for the check there if I block. Okay, I went for an exchange, another exchange. Because bishops and knights were equal, it had no problem making that exchange. All right, now if I block here, it's going to move the queen back. It's not going to give up that exchange. Let's see what it does here. All right, I had a pawn hanging there, so it went and captured it. And now it's going for the rook next. So even if I block it here, it's going to capture that there. I can block it here. It's going to take the piece there rather than exchanging. That gave it a +1. So it's making pretty good moves here already. And now now you might be wondering why it's moving the queen around so much. Now because there's so many queen moves, when we shuffle it, it's very likely that a queen move comes to the top. Like versus like this knight only has 1 move, this knight has 3 moves. So it's more likely to pick a queen move versus any of the other ones, right? So that's why it's moving that queen around a lot, seemingly randomly here. All right. So let's do this. Okay. Yeah, I mean, it's playing pretty smart right now. We could even value like checks as being more valuable too. So like that's another thing you can add. Like, can you put your opponent in check? Maybe evaluate those moves first. And there it goes, found the checkmate. So that was a pretty solid game already, and we're only looking at 2 moves in advance. So I'm gonna end this video here. One thing with this algorithm that you see, it's a little bit confusing because we have 2 for loops and they're nested within each other and they're kind of doing the same thing. It's like making a move and then we eventually get to this base case where we store the score of that algorithm. So what we're going to do in the next video is we're going to implement this similar idea, but we're going to implement it recursively. And then this will allow us to go to higher depths. So right now we can only go look 2 moves in advance. And if we were to make a 3rd move in advance, we could certainly do that. We'd basically have to make another for loop with our possible moves and then evaluate the board at that position and then pick the maximum of those moves, because then those are our moves. And then you can see how like the opponent would want to minimize our maximum and we want to minimize their maximum. And so it gets pretty convoluted to try to do it without recursion. Even this was, I think conceptually was, hopefully seeing it with for loops helps you out. I wanted to do it this way, even though this is not the best way to write this algorithm. It's a lot cleaner when we actually move to the actual algorithm, which I'll have that. I'll do that with the next video, and then we'll look at how can we prune off branches that we don't need to look at. So moves that are kind of meaningless, like we shouldn't even evaluate those moves. Let's only look at the important ones. So yeah, we'll get into that in the future videos. I hope you guys enjoyed this one. Feel free to, at this point, try and make your AI a little bit smarter. Maybe play with checks a little bit, or maybe play with positions and see if you can modify this score algorithm to like make it a little bit smarter. And you'll already see that your chess engine will improve. So, all right, that's all I got for you. Let's end with a game of chess between our AI. So let's see this beautiful game between our 2 pieces. And this should be a little bit better than our other random game, which didn't seem to make a whole lot of sense. White is dominating, just gobbling all the pieces. Another thing we could look for, like right now, white could easily push one of these pawns. Oh, it went for a stalemate. That's a bug. That should be fixed. But we'll get to that later. All right. I hope you guys enjoy your weekend, and if you have a long 3-day weekend, I hope you guys can enjoy that. Until next time, I'll see you.